topic that we're going to talk about today is what you can see in the sky with just your naked eye. So just looking up at the sky, no binoculars, no telescopes. And so this is a really good kind of tie-in with history too, because we'll talk about what ancient people saw in the sky as well. We'll talk about, so let's preface what we're going to talk about today. So we're going to talk about what the universe looks like from the Earth. We'll talk about why things like stars rise and set, and then we'll talk about constellations and how what you can see in the sky changes throughout the year. So what does the universe look like from the Earth? So this is a picture of the sky that somebody took with their camera. So this is the exposure time of this image is longer than what your eye might see. But if you go to a dark enough place, you can see this band of extra stars in the night sky, and that's the Milky Way galaxy. So that's our galaxy that we reside in, and we're inside of the galaxy, so we're seeing basically a bunch of the other stars that are in our same galaxy. And there's so many stars in this band of the sky compared to elsewhere that it looks like somebody spilled milk across the sky, so that's why it's called the Milky Way. We'll come back to talking about light pollution a bit later in the class, but even out here in Illinois, it's not as dark as you might think. So you kind of have to go out in the country a little bit before you can start seeing the Milky Way. Okay, so constellations are, this is kind of something that people misassign this vocab word for. So constellations are just regions of the sky. So there are 88 constellations that fill the entire sky. The thing that you might think is a constellation, which are the shapes that you make by connecting stars with different lines, those are actually called asterisms. So Orion is the hunter. This is Orion's belt. The area of the sky that this asterism lives in is the constellation Orion, but the actual stars themselves that you connect to make the shapes are asterisms. So a bit later in the class we'll talk about coordinate systems, but before we had more modern coordinate systems for mapping locations of objects in the sky, you would say, hey, I found this really interesting object in the constellation of Canis Major. And so people would know what region of the sky they're in because they would find that asterism, and then they would look in that region of the sky. So before modern technology, that's how you would tell people where something was in the sky. You would refer to the constellation, and then they would know what part of the sky they should be looking in. So here's a conceptual question. So what can we say about the brightest stars in a constellation with respect to the other stars in the same constellation? Right, so when you look up at the sky, what you're actually seeing is a two-dimensional projection of a three-dimensional space. So if I was in a spaceship and I wanted to fly to some star, I would have to not just leave the Earth's atmosphere, but I would have to keep going some distance in space. So all of the stars in a constellation, from Earth, they look like they might be close by on the sky, but when you add that third dimension of space that you need to travel through, they might be actually quite far away from each other. And so because they're far away from each other, that means they're not going to be the same age because they didn't all they weren't all born in the same stellar nebula, and again, they might be at different coordinates in the depth direction, whereas they look like they're close by in the XY plane of the sky. Okay, so if we want to be a bit more precise with how we talk about where things are in the sky, we can develop some more vocabulary words. So instead of just talking about what constellation an object is in, we can start to build up a coordinate system. So the celestial sphere is basically if you took just a sphere around the Earth and plotted where things lie on that sphere. So again, this is still just the 2D projection. We're not worrying about is this star really further out this way or closer in this way. So this is still the 2D projection. So that's what the first bullet is saying, that all of these stars that might be different distances away, they all appear to be at the same surface on the sphere. The ecliptic, so if we take the Earth's equator and we extend that line out to the celestial sphere, that is the celestial equator. The ecliptic is the plane that the Earth orbits the sun. So remember, the Earth's axis is tilted 23.5 degrees compared to the plane that it orbits the sun, and this is a good visualization of that. So if the Earth's axis wasn't tilted, then the ecliptic and the celestial equator would be the same circle. But because of the tilt to that axis, the equator is not aligned to the ecliptic. Then if we take the North Pole and South Pole of the Earth and just extend that outwards, those would be the North Celestial Pole and the South Celestial Pole. Okay, so then we can plot all of those constellations onto our celestial sphere now. So there are constellations that are near the North Celestial Pole, there's constellations that are around the celestial equator, and then of course there are constellations around the South Celestial Pole. So many of the constellations around the celestial equator you might recognize, like Taurus, Aries, Aquarius, and around the ecliptic. So those are all of the horoscope star sign kind of things. And so that's the origin of those star signs. We'll talk about what it means if you were born as a Taurus or something a bit later today. So the Milky Way is this band of very dense stars that you can see when you go into a dark place where the sky is very dark, and that's the galaxy that we live in, and that's our view of the galaxy looking through the plane of the galaxy. So if we're looking over here, we're actually looking either above or below the plane of the galaxy. And so we don't see quite as many stars. Okay, so if we are here in the Milky Way, when you look towards the celestial North Pole or the celestial South Pole, you're not looking through the disk of the galaxy, so you're going to see much less stars. But if you look towards the celestial equator or the ecliptic, then you're looking through the disk of the galaxy, and so you see a lot more stars. And that plane of the galaxy is the galactic plane. Okay, so that's how you can talk about kind of where things are in the sky using, I guess we'll call it like astronomy terminology. But now let's say I'm standing next to you on the ground and I want to give you like numbers and angles and tell you where to look in the sky to see this interesting thing I just saw. So your local sky, there's several different vocab words that we'll introduce. If you're standing, wherever you're standing, and you draw a line straight above you, that's called zenith. Typically, we'll measure our angles from the horizon. So if you draw a line kind of along the ground to where it meets the sky, that will be your horizon. And then we'll measure our angles up from the horizon. So that angle is called the altitude. So if something is 60 degrees above the horizon, it will be at an altitude of 60 degrees. If something is directly overhead, you would say that has an altitude of 90 degrees. So you're just measuring the angle between the horizon and the point on the sky. Okay. But if I just give you an angle above the horizon, I haven't told you which way you should be looking before you start looking up in the sky. So in addition to the altitude angle, you need to tell people what direction they need to be facing. So this person is facing southeast, so they're facing somewhere in between the cardinal directions of south and east. And so they face southeast and they look 60 degrees above the horizon, and they'll see whatever interesting thing is there. Maybe it's a plane or a satellite or something. So this is very useful if you are in the same part of the earth as someone else. So if your friend is standing right next to you, you can tell them where on the sky they should look. But what if I'm an astronomer and I discover something really cool in the night sky in Illinois, and I tell someone in Hawaii to look at the same thing with their telescope? I can't tell them these same things because they're not in the same place on the earth. So a bit later in the semester, we'll talk about how we develop a coordinate system that will work for everyone, no matter where they are on the earth. Yeah, so that's just defining all of those words that we talked about: zenith, horizon, and meridian. Oh, I guess I didn't talk about meridian. So if you connect basically make a hemisphere or a semicircle going from due north to south, going through the zenith point, that will be the meridian. Here's kind of in more detail how you can measure angles on the sky without like breaking out a protractor. So for kind of a rule of thumb, the moon and the sun are about half a degree angular diameter in the sky. So if you see something that's about the size of the moon, then that would cover half a degree. In the northern hemisphere, the angle between the two stars of this side of the Big Dipper are about 5 degrees apart. And if you're in the southern hemisphere, the tips of the Southern Cross are about 6 degrees apart. You can use your hand as a protractor basically to measure different angles. So if you spread your hand out in front of you, then the distance between your thumb and your pinky is about 20 degrees, and the width of your index finger is about 1 degree. If you hold your fist out in front of you, then the width of your hand is about 10 degrees. So especially for your sunset project, if you want to measure, let's say you measured your first sunset and it went to the left of a building, and then the next observation it was to the right of the building, you would say maybe that was 2 fists away, and so that was 20 degrees that one sunset differed from the other sunset. And then you can also measure like the distances between stars in the sky, and maybe there's something interesting next to a really bright star, so you can say, look, 5 degrees away from this really bright star, and you can see maybe there's like a satellite or something. When we are measuring angles, a degree is actually a pretty big angle in terms of astronomy, and so we need to break that angle into smaller measurements so we can be more precise. So 1 degree is so there's 360 degrees in the whole circle. So 1 degree is a pretty small slice of a circle, but for astronomy to get really precise, you need to go into what we call arc minutes. So there are 60 arc minutes in 1 degree. And even arc minutes are not terribly precise. So when we talk about the positions of stars in the sky, we can get down to arc second precision. So arc seconds, there are 60 arc seconds in 1 arc minute. And so it's the same kind of scale factor going from degree to arc minute, and then arc minute to arc seconds. So it's basically asking you to convert 1 degree into arc seconds. Okay, so this will be a good example of a technique that I'll call dimensional analysis. Or you might also see it called stoichiometry in chemistry. And so for this question, we want to go from 1 degree, and we want to know how many arc seconds that is. So we're basically doing a unit conversion. So 1 degree we want that, first we're going to go into arc minutes, and then we'll go into arc seconds. So how many arc minutes did we say were in 1 degree? Okay, 60. So what I'm doing here, and maybe for a different example, I'll use a different number. So let's say I ask for how many arc seconds were in 2 degrees. So I start by writing the unit or the number I want to convert, and then I just multiply by a factor that equals 1. So 60 arc minutes is the same thing as 1 degree. So if I make this a fraction, I'm really just saying I'm multiplying by something where if I cancel these out, this is just multiplying by 1. So I haven't changed the value of anything, I've just changed the units. So now the things that are on top, I can cancel those units out, and I'm left with units of arc minutes. But we wanted arc seconds, so we'll do the process again. So I need something that has arc minutes in the bottom so that I can cancel those units out, and I want to end up with units of arc seconds in the numerator. So we just do another conversion factor. So how many arc seconds are there in 1 arc minute? 60. So now I can cancel out my arc minutes, and I'm left with whatever number I started with, which if we did a different example, it would be 2. If we go back to the original example, it was 1. So now I just take all of my numbers in the numerator and multiply them together. So I have 1 times 60 times 60, so 60 times 60 is 3,600. And then in the bottom, all that was left is 1, so if I divide by 1, It doesn't change the number. So this is how we can, this is one of the techniques that you can use to convert units. Okay. Yeah, so this technique is going to be useful. There's going to be a lot of units that we talk about, especially when we talk about distances, and being able to convert between different distance units will be very important. Okay, so if we go back to thinking about the celestial equator, or the celestial sphere, the celestial equator, and the celestial poles, we can start talking about why stars rise and set. So we know that the Earth rotates on its axis, and so on Earth it looks like stars and planets are moving throughout the night sky, but it's really the Earth rotating on its axis causing the motion, the apparent motion of those things. So those things, some of the things are moving, like the planets, but for the most part, the stars are not moving very much, and it's really the Earth's rotation that's causing these large apparent motions of these skies. So this is a time-lapse photo of the night sky at the Delicate Arch. So one of these bands is just one star, and the motion of the Earth has caused the position of the star in the sky to change over time. So this streak is just the position of one star as it appears to move across the sky. Okay, so so being on the Earth, what is our view of the sky like? So there are some stars that are always above the horizon, so we can always see them in the sky. And so right now there are stars in the sky. It's just that the sun is much brighter than those stars, so you can't see them when the sun is out. So even in the daytime, these circumpolar stars are always in the sky, but the sun might be so bright that we can't see them. And so circumpolar stars, they are going around the pole, so that's why they're circumpolar, and they're always above the horizon. Then if we go a bit farther away from the celestial pole, there will be some stars that are above the horizon sometimes, and then below the horizon other times. So these stars, even if it's nighttime, you might not be able to see them because they might be below the horizon. Then if we go past the celestial equator, again, there will be some stars that are sometimes above the horizon and sometimes below the horizon. But then if we go close to the south celestial pole, there will be circumpolar stars down there that we never get to see in the northern hemisphere. So the night sky in the northern hemisphere and the southern hemisphere actually looks different. So there will be constellations that we can see in the northern hemisphere that people can't see in the southern hemisphere, and vice versa. And so that's very important for doing astronomical research, because maybe a supernova explosion happens down here, and if you don't have telescopes in the southern hemisphere, you'll never be able to study that supernova. So it's important to have your telescopes distributed across the northern and southern hemispheres so you can have the best chance of studying interesting stuff when it happens. And so just like so these stars will rise and set, and so will the sun and the moon and different planets, again because of the rotation of the Earth, not necessarily the motion of those objects. So if we go back to this picture of the time lapse taken at the Delicate Arch, what is the arrow pointing at in the middle of the arch? Yeah, so if we go back to the picture, zenith would be above the arch. So if you're standing here, you would draw a line above your head, and zenith would be right above you. The celestial equator, so you can kind of see it being mapped out by the streaks of the stars. So the celestial equator would kind of be the plane basically that you're looking at the photo. And the ecliptic is similar to the celestial equator, but they're offset from each other by 23 degrees. So those would be planes more or less in the plane that you're looking at the photo. So the celestial North Pole is what the arrow is pointing at. So remember, the Earth is spinning on its axis, and so that makes it appear as though stars are doing these circular motions in the night sky. And what they are circling around is the celestial North Pole. Okay, so we talked about how your view of the sky can change whether you're in the northern or the southern hemisphere, but what you can see in the night sky will also change depending on what time of year it is. So here's a diagram of the position of the Earth with respect to the sun at different times of the year. So remember, the Earth is going around the sun. And so at different times of the year, so let's start maybe at January, the beginning of the year. So as you look towards the sun, that would be daytime. So in the daytime here, anything that's in the same part of the sky as the sun, so that would be everything on the right-hand side of the diagram. The sun is bright, and so you're not going to be able to see these fainter stars behind this very bright sun in the sky. So in January, you're not going to be able to see the constellations Aquarius, Capricorn, Sagittarius, but you can see Cancer, Gemini, Leo, etc. But then as we go through the year, let's jump ahead by 6 months to July. Now in July, if I'm looking towards the sun, that would be daytime, and Cancer and Leo and Gemini are behind the sun, and so the sun is too bright and we're not going to be able to see these fainter stars behind the sun. But now we can see Capricorn and Aquarius and Sagittarius. Okay, so if you are familiar with the zodiac or horoscopes at all, then for example, I'm an Aries, but March, you would expect Aries to be over here, right? Like, I can't see Aries during March. So the way that horoscopes were actually developed is what constellation is the sun in at noon on the days that you're born. So you can't actually see the constellation that goes with your horoscope sign at night during your birthday month, basically. So it's where the sun is at noon at those times. And you'll also notice that it's shifted a little bit. So you would expect Aries to be directly behind here, because that's March, end of March, beginning of April is the kind of the cutoff for that. And we'll talk about why that is probably at the beginning of next class. So there's something that's causing the horoscopes to no longer line up with what they were when they were originally established. So I, as a scientist, don't really put much credence into horoscopes and star signs, but I will say that as a society, there are people who put emphasis into those things, and so just the fact that people do believe in it can actually have an impact on society as a whole. So, which I think is kind of an interesting interplay between science and psychology and society. Okay, so we have developed a coordinate system to describe where we are on the Earth. So we defined the zero, so there's these lines, imaginary lines that we draw on the Earth, latitude, which go around the globe in this direction, and they increase going from north to south. So 0 degrees latitude is the equator. And then as you go closer towards the North Pole, your latitude increases. And conversely, your latitude will either, depending on the coordinate system, will either get negative as you go towards the South Pole, or we just use the same number as we do in the North Pole, and we put an S or an N so you know which one is north and which one is south. And then longitude, longitudinal lines connect the North Pole and the South Pole, and we just kind of arbitrarily assigned a 0 point. So the equator being the 0 point for latitude, that kind of makes sense, but there isn't an equivalent equator in the opposite direction. So the kind of the scientific and cultural power at the time when this was decided was England, and so they got to decide that the 0 line for longitude went through Greenwich, England. And so using latitude and longitude, you can define where you are on the Earth using those two coordinate numbers. And later on in the semester, we'll talk about how we can basically project these latitude and longitudes onto the sky and develop our own coordinate system for astronomy. So going back to how the sky changes in latitude and longitude. So the sky, what you can see in the sky varies with latitude, but it doesn't change with longitude. So where we are in America and the same latitude in Europe, they might not be able to see, so it might be daytime here and nighttime there or vice versa, but eventually the Earth will rotate such that whatever we could see in the night sky in America, Europe will be able to see in their night sky as well. So it might take a few hours for the day-night cycle to match up, but they will be able to see it. Whereas if I see something in America, somebody very close to the South Pole might never be able to see that thing ever. So latitude is the thing that matters for determining what you can see, and not longitude. Okay, so this could be useful if you ever get lost in the woods at some point. In the northern hemisphere, this is a lot easier than the southern hemisphere. In the northern hemisphere, if you can locate the asterisms of the Big Dipper or the Little Dipper, then you can find Polaris, which is the North Star. So we talked about the celestial North Pole. There's no reason that there has to be a bright star at the celestial North Pole. So we as a human society have just been very lucky that there happens to be a relatively bright star very close to the celestial North Pole. So if you're trying to navigate by, like, let's say you're sailing and you don't have GPS, how do you figure out where you are on the Earth and what direction you're going? So maybe in the daytime, you can see the sun rising and setting, and you can kind of figure out east and west. But what do you do at night? And how do you determine your latitude? So you can use astronomy to figure out your latitude by studying the star Polaris. So either finding the edge of the handle of the Little Dipper, or using the cup of the Big Dipper to point towards Polaris. If you measure the altitude of Polaris above the horizon, that will tell you what your latitude is. So if I get lost in the woods, or I get kidnapped and dumped some random place, hopefully in the northern hemisphere, then I can at least figure out my latitude by measuring. Maybe I just use my fists and I stack them on top of each other, and let's say I measured 5 fists. One fist was how many degrees? 10. So that would mean the Polaris is at an altitude of 50 degrees, and I would know my latitude would be 50 degrees north. So this is what people did to navigate at night before we had more modern technologies. In the southern hemisphere, it's a lot harder. There is not a bright star located at the southern celestial pole. What they have instead is the Southern Cross, and you can use where the cross is pointing, and over time kind of zero in on where the south celestial pole is. But you can see this takes kind of a lot of time to really get a good, and it would just be an approximation of where the south celestial pole is, whereas if you can find Polaris, you can do that measurement pretty quickly. So my advice is don't get lost in the southern hemisphere, and if you have to get lost somewhere, do it in the northern hemisphere. So let's say you're lost in the woods and you see the North Star is 40 degrees above the horizon. What latitude, or where are you on the Earth? Yeah, you would be at 40 north latitude. At the North Pole, the North Star is directly above your head. At the equator, the North Star will be along the horizon, and the longitude one was just there to throw you off if you confused it with latitude. Okay, so we can see our own galaxy from very dark places on the Earth, and we can talk about positions of things in the sky either using constellations, or we can use things like altitude and directions. And things appear to move through the sky because of Earth's rotation. We can see different constellations depending either on the time of year, or your latitude will determine what things you can or can't see. Okay, so we'll talk about seasons next. So what causes seasons, and So true or false? Earth is closer to the sun in the summer, which makes it warmer, and farther from the sun in the winter, which causes it to be colder. Yeah, so this is false. So this is a very common misconception that people have. Just a summary, this is basically doing a bunch of interviews of Harvard graduates asking them the same question. And a lot of them gave similar answers, saying that it's because the Earth is sometimes closer to the sun and sometimes further away, causing the seasons. And so Harvard graduates, you would think these are pretty smart people, but they also have these misconceptions about what causes seasons. So it's not that the Earth is sometimes farther or closer to the sun, it's due to the tilted axis of rotation of the Earth. So the Earth does have a very slightly elliptical orbit, meaning it's not quite circular, but it's not nearly elliptical enough to cause the changes that we experience for the seasons. So instead, what causes the seasons is whether you're receiving direct or indirect sunlight. So if we're in the northern hemisphere, during the southern months, the northern hemisphere is pointed more directly towards the sun, and so we get, if you look at, let's say, these 5 light rays, they're distributed over a smaller area than in the winter time. We're not pointed directly at the sun in the northern hemisphere, and so those same light rays are spread out over a much larger area. So the same amount of energy over a larger area means that it's less effectively going to heat that part of the Earth. And if you have traveled a lot, or maybe you have family, or have friends in the southern hemisphere, when we in the northern hemisphere are having summer, they're having winter. So the seasons are flipped depending on which hemisphere you're in. Because if in the summer we're pointing towards the sun, then that means that people in the southern hemisphere have to be pointing away from the sun, or less directly towards the sun. So here's the northern hemisphere summer, so we're getting the direct sunlight, but in the southern hemisphere you can see it would be at an angle, so it's less direct sunlight, less able to effectively heat that part of the Earth. But if you're near the equator, you're pretty much going to get direct sunlight year-round. And so these lines that we've drawn, the Tropic of Cancer and the Tropic of Capricorn, those latitude lines are basically the boundaries of where you're pretty much always receiving. Between these latitudes, it's usually similar temperatures year-round. Then when we flip it in the winter time for the northern hemisphere, so now we're not receiving that direct sunlight, but the southern hemisphere is receiving the direct sunlight. So the big takeaway here is that it's the angle of the Earth's rotation about its axis that causes seasons. It's not the distance between the Earth and the sun. Because of the angle of the Earth's rotation, where the sun, so if you look at the highest point that the sun reaches in the sky on any given day, and you were to plot that position over the course of the year, the sun actually, where it reaches its highest point in the sky, changes throughout the year. So in the winter time, the sun doesn't make it nearly as high in the sky as it does in the summertime. Okay, so maybe we'll just do a minute of thinking about this, but the longest day in the northern hemisphere is June 20th. Is June 20th normally the hottest day of the year? Or are there hotter days after that? And when do temperatures actually start to decrease after the the longest day when you would expect to have the most sunlight. So maybe with the person next to you can talk about that for a little bit, and then we'll come back together as a class. Okay, so what is this the hottest day of the year? No. And it doesn't start getting cooler until much later than that. So does anyone have an idea why? So the reason why it takes a while for the Earth to start cooling down after the longest day is we have an atmosphere. So the atmosphere traps the heat, and it takes a long time for the heat to dissipate, basically. So the atmosphere kind of acts as a resistor to changes in the temperature of the Earth. So even though the hottest day is in June, summer lasts until August, basically. So the seasons they actually lag a little bit where you might expect them to be.